This
on
conference
VFDs.
will now be recorded.
Sorry, I just
So,
hit the record button because I forgot.
okay. So anyway, the APA got involved. So now they've created a problem. You're making the motors more efficient, which is drawing more energy. You're not changing the frame sizes, and you're changing the characteristics of the motor, and then you're changing the insulation characteristics of the motor. So then we throw in, the Clean Water Act, and I forgot when that came into play, but that was the one where you could no longer use bronze impellers. So everybody went from a bronze impeller to either a stainless steel stamped impeller or a plastic impeller. Well,
And
what happened there was that you lost the flywheel.
Craig, tell me this. What was the problem with bronze in water?
They felt that it contained too much lead.
Oh, okay. Okay.
So that's why they decided that they were going to get rid of it. So now you lost the inertial mass, well, of the rotor. Well, that was the last key, because when you made the motor more energy efficient, what they did was I don't know if you guys noticed, but if you work on any large horsepower motors, it's very apparent when you look at a 250 horsepower or 300 horsepower from 10 years ago versus one from last week. There's a substantial difference in the iron and copper. I mean, those units are like, 30% smaller than the previous generation of motors, well, a couple generations back. So again, you're losing rotor mass. Now, as we've talked in previous classes, drives aren't the greatest things for motors. They're great for energy saving and doing what they're supposed to do, but they put out a pulse width modulated output. So rather than a nice, smooth, continuous sinusoidal power supply, you're getting this choppy one. So the motor's kind of starting and stopping as it goes around. I guess I have to do it slower. So it makes notching. It basically kind of cogs around at a very high frequency. Well, so you're kicking the motor every time with an electric pulse. So if you have the rotor mass in the old days, that was no problem. But as soon as they went to the efficient and super efficient motors, you lost rotor mass. And then it was okay, but then when you lost the impeller mass, then we started having a problem. Because what was happening is that when you're pushing that column of water up and you've got the missing mass of a flywheel effect on a submersible pump, you're getting basically a torque ripple. So the motor is stalling and then hitting it again, and then stalling and hitting it again. And so they figured out, okay, that's why it's causing the motor to do a turn-to-turn burnout. So then the motor manufacturers, or the submersible manufacturers, came up with, well, let's encapsulate the windings. So we're going to lose the cooling effect of the water circulating around the windings, because the water in contact with low VOC varnish was causing it to soften up. Well, they encapsulated.
Just a second, Craig. I put an image up here. If you can see, can you see this image properly?
Yes.
Okay. I hope it's not too small. But what Craig's talking about in terms of the smooth sine wave versus the bumpy sine wave, and what it does to the submersible motor operation, what it does to any motor operation, frankly, is if you look at the blue line here, that's the perfect sine wave. And if you look at these various colored waveforms other than blue, you'll see that they're not quite sinusoidal. And this is an almost sine wave, which is what standard VFDs that we've been using since 1983 accomplish without filters. Now, you get back to the blue waveform when you put a sine wave filter on the output of the VFD to the motor. And in this case, we're talking submersible motors. But this bumpy effect here is not necessarily noticeable to humans, but it is, as Craig said earlier, a higher frequency. And what it does is it causes the motor to be less efficient. Craig, go ahead.
Yep. So the less efficient part is, when they encapsulated the motors, the less efficient part causes overheating. Now, I was lucky, and unfortunately, I wasn't able to take pictures of it because that was prohibited. But I saw a submersible motor cut in half lengthwise. And what I saw was very interesting, because the windings are no longer being cooled by water. They're looking at standard convection to radiate the energy out, the heat. But if you put it in an encapsulated epoxy, epoxy is an excellent insulator. So what I saw was from the center going out, it looked like basically an overload condition on a motor. I mean, you get that dark brown in the middle, and then it goes out to tan, and then back down to its normal color. So
Hmm.
that's what I started seeing, and um, we're figuring out why motors are cooking themselves is because all this stuff happened. I mean, we've got the DOT or DOE getting into it. We got the EPA into it. We get the state of California in it, and you get these poor pump and motor manufacturers stuck in the middle. They're regulated to build these motors as a bunch of bureaucrats that have no idea from their ass from a hole in the ground, that this is going to cause us this cascading problem. In fact,
Okay.
in U.S. Motor vertical hollow shaft, I think it's actually not even vertical hollow shaft. It calls it their motor suitability guide for VFDs. At the very back of it, almost the last paragraph, there's a statement in there saying that you basically, from now on with their motors, you have to make sure that you have heaters in them to keep the windings dry, and then every year go out with dry compressed air, which is very expensive. That means that you have to put a refrigeration system on it to remove moisture from it as the air gets compressed. It gets wet, and that's why you always have to have your water filters and everything. But they want it on extra step. They want you to run it through a refrigeration dryer before you blow the motor out. And they want that done every season before you start it up. And then they want you to run those heaters for a week before you bump the motor. And we have a document that says that.
And the document is coming from which company?
US Motors.
Interesting. That's the vertical turbine
It's
people.
actually called, I think it's called the Motor Suitability document. I'll send
Okay.
one to you, Pierce.
And they're now owned by Nidec.
Yeah.
Did General Electric put out a similar document?
No, they would never admit to it. But I was on a study. Remember when I first came on, I was on a study, and there was a large sum of money paid out to a customer under goodwill. Never an admission of guilt, never admission of failure of motor. But they used pretty much everything in the study that they went, and that was with Danny Peters and Knox Johnson. And so we had a third party guy doing the checking of everything with a scope and a power analyzer, and we came to the conclusion that we were well within NEMA MG1 guidelines for VFDs on motors.
The third party guy being Knox Johnson from
Knox
Control
Johnson.
Concepts.
Yeah, Danny Peters and I did not touch the metering stuff. Only
Well,
not.
I remember that study. In fairness, did we not determine that a lot of the failures in this were due to the fact that if the people had hooked up the space heaters, they would have been fine?
We found, sorry, we found that on the ones that were all vertical hollows, but the ones that were submersibles, we actually had one site that was checked that we discovered that after tracing the wires back, that the motors that were failing, excuse me, had been installed on across the line starters.
Oh, okay, very good. So let's do a short summary of what we've talked about here. We're talking about this, giving you an update on where we are at in terms of the submersible pump motor applied on a VFD, and we've had an unacceptable level of issues. Certainly unacceptable to the motor manufacturers because a lot of it is happening within their warranty periods. And basically, the goal at Yaskawa is that a motor will run as long on a VFD as it will on a contactor. And that's sort of a general goal, okay? Probably not technically sound because varying the speed of the motor versus running it across the line all the time is not a fair comparison. but I think you understand the intent. So submersible motors were exhibiting much more problems than was and would be in any situation acceptable. And as we all started delving into it in the industry, the manufacturers, the distributors, the end users, Yaskawa, the other drive manufacturers, what we've understood to be the case now is that the submersible motors are not failing all the time on DVDT or voltage spiking issues in the windings. We're seeing a significant number of thermal failures. So that's what led to this investigation, if you will, because we really need to solve this problem for the industry. More and more of these submersibles are going on VFDs for very good reasons. You need to vary the speed on your pumps, and therefore you need a variable frequency drive. So the immediate solution when we suspected DVDT or voltage spiking was to use a DVDT filter on the output of the standard VFD. And that's called a low pass filter. And what it does is did I say that right? Yes. It filters out all the high frequency DVDT voltage spikes and allows the low frequency, low pass filter, which is the 60 hertz signal, to pass through. So we still had failures. And with these DVDT filters, and we're looking at the waveforms and we're saying, wait a minute, this isn't right. We have a filter. And I think that the motor shops didn't come back to us with correct autopsy data. They were kind of rubber stamping DVDT voltage spike whenever they had a failure on a VFD. And then we started to look into it and we realized, no, these are thermal failures. As Craig said, they split open a motor. He looked at it. He saw the standard and classic evidence of a thermal issue. Looking into it more, and I think to their credit, Franklin did some good work here. We realized that for a variety of reasons, these motors were failing thermally. They were overheating. Now, the initial thing that I got, not being in the mix as much as Craig was that these motors, because of their lower inertia, don't ride through the harmonics of the waveform that they're receiving from the VFD, as well as a big fat above ground turbine motor, because turbine motors are NEMA motors and they tend to be shorter and wider, therefore they have big inertia. And that inertia helps them to ride through the aberrations that are associated with this waveform that you see on your screen. What Craig came up with was something even more interesting. The issue of riding through the harmonics on the waveform that the VFD sends to the submersible motor. Initially, we thought, oh, okay, that's understandable because the motor's long and skinny. It has less inertia. But what Craig brought to light is that the problem was even more exacerbated by, one, the fact that the federal government energy efficiency standards caused the motors to be redesigned so that they have a slightly higher full load RPM, causing them to go faster, and in a pumping application, that means they're going to draw more power by the cube, if you will. Morning, Larry. And the second issue is that because moving away from bronze impellers and to lower inertia impellers, we've now further reduced the inertia of this motor, so it's even more susceptible to the aberrations that are associated with the harmonics from the VFD waveform. And then lastly, the mandating of low VOC insulation, which means that the insulation cannot be exposed directly to water, has to be epoxy encapsulated. So now you have more thermal losses in this low inertia motor because of the VFD waveform. And now you're trapping those additional thermal losses onto the winding with the epoxy encapsulation. A concert of left turns that has resulted in significant problems in the submersible motor application. So with all that said, we think we understand the issue. And we now are seeing that the manufacturers are, I'm seeing in their terminology, Craig, recommendation. I'm not seeing anybody overtly coming out and saying, if you do not use a sine wave filter, we will not honor the warranty. Have you seen that?
Yes, I've seen that. Grundfos has actually got that verbiage in their literature. Most of the vertical Hall shaft guys have it in their literature, but what we find is that the field reps are kind of easing everybody into it, because when you put a sine wave filter on the back end of a drive, you're basically doubling the cost of the installation. And the thing that's ironic about it is, I want to point out about the size difference between, say, a 250 of 10 years ago and a 250 of now is, if you look at the weight of the motors, if you add the weight of the DVD filter, which is basically iron and copper, back into the weight with the motor, the new motor, you'll actually equal or get close approximation of the weight of the old motor. And that's because you're adding the impedance back in the line, which was lowering the DVD spikes. It was absorbing.
But you're not getting the benefit of the inertia in the motor, because the extra weight, extra mass is in a filter that's up on the surface and it's not rotating. Okay, so that's the problem. The solution.
I just want to point out one other thing. I ran across a gentleman a couple of years ago that was out of San Diego, and they started suddenly losing 3 horsepower, 2 and 3 horsepower submersible motors in a residential area. It was driving him nuts. And they were all across the line starters. They were using Franklin controllers. And what we came up with is, I said, check and see if you've got new solar farms nearby, which they did. They had 2 of them installed nearby. And the next year he came back we were at the California Groundwater Association's conference. He came back and he says, yeah, we did power analysis of our waveform coming out of a transformer, coming, basically the line side. And he was getting spikes, because apparently PG&E, Southern Cal Edison, and a bunch of other people did not realize that on their inverters for their solar ranches, they needed to have filtration. Well, low bidder always takes that out. So they were getting harmonics created by their inverters on the solar farms coming to the motors, blowing them out. So he asked me for my solution, and I said, well, it's going to sound really stupid, but you need to put either a DVT filter or a sine wave filter on those motors. And he did that, and it stopped the problem.
Okay, so that's interesting, because even without a VFD, if you have power line harmonics, such as what you see here in this diagram, where we're not talking about a nice blue sine wave, what we're talking about is one of the other waveforms, you need to filter it. So in the case where the power company is causing the harmonics, even though you have a contactor, no VFD, your submersible motor could be at risk, and you're going to have to filter that input. I think what we're seeing now is that because of the change in the insulation, the inability for the motor to dissipate as much heat, because of the lower inertia, which makes the motor much more vulnerable to harmonics or aberrations on the sine wave, the motors need sine waves. And there's a lot of data now that's telling us that this is the case. So the solution, if you're using a standard VFD, you're going to have to use a sine wave filter to get the full life out of your submersible motor. No ifs, ands, or buts about it, I think. And I think that the manufacturers on both sides are coming out and agreeing with that. Certainly, if the statements are such that we're not honoring warranty until you put a sine wave filter on the output of the VFD, that's a pretty conclusive statement. So moving on, Craig is right. You put a sine wave filter on the output of a VFD, it's not only a high pass filter, it's also a low pass filter. So it's kind of a double filter. and it's expensive. It's about the cost of the VFD, so you've doubled the purchase price. I'm going to disagree a little bit with my colleague on the installation costs. I'm going to say that the installation costs are probably more than double because of the extra piping, the weight of this thing, the fact that you've got to put it into an additional space, so you're taking up more real estate. But the real cost of these filters, quite frankly, is the efficiency. Craig, what do you say, 2 to 3% tag on the energy bill?
Oh, at least 3% at minimum.
Okay, so this is the situation we have. At Yaskawa, we try to find a better way of doing things, and the update that I wanted to give you, this has been a great discussion. It took a lot more time than I thought it was, so we're going to probably push some of the other subjects to next week. But this is a very important subject. Yaskawa has a solution that we're testing in the field because while we're very aware of the output of our matrix drive, this is the IQU 1000 product, and we claim that the harmonics to the motor without a filter are very low. Therefore, we don't need a sine wave filter on the output of our matrix drive the way we would need a sine wave filter on the output of our standard IQ 1000, just like everybody else who's using a diode front end 6 transistor VFD, the standard VFD. With the matrix drive, we have data and experience that tells us we do not need a filter to produce a sine wave. We see it on an oscilloscope. Not to rush out and say, okay, everybody use matrix drives, because that's not who we are. We're very conservative in terms of what we want to say to the marketplace. We're going to be testing. We're going to have an installation up in the Fresno area. We're going to have an installation up in the Santa Barbara area. These are going to be 125, 150 horsepower submersibles. We're going to put matrix drives on them, and we're going to run them. We'll keep you updated on this class as to how that's going, and we'll report the results, of course, good or bad. This is not a sales class. This is a technical class, and in this venue, we want to be truthful in terms of what's best for you to pump water. Okay, that's the update on the submersibles. I want to take a few minutes to talk to you and to start a two-way conversation in this class that I will ask to continue throughout, the following weeks. Wireless control. I'm trying to get a better understanding of what's required for wireless control. A lot of wireless control is coming into the field. I'm seeing all kinds of different methods of accomplishing it. What I'm also seeing is a relatively inconsistent level of quality and utility, primarily associated with the signaling integrity, and then secondarily with the utility of the graphical user interface, the GUI as the software nerds call it, that you get on your cell phone, laptop, tablet when you communicate wirelessly through the internet or some other network method to the remote location. So what we're talking about here is, that's the troubleshooting class. We're not going to get to that. What we're talking about is a device that looks something like this. And this happens to be a weatherproof unit IP67, which means you can dunk it in 1 meter of water. So it's very suitable for just sticking on the side of the VFD can. And I put a sunshade on it because ultraviolet will eventually tag that screen. And you wire it directly to the VFD via a Modbus serial connection. So the goal of wireless control for this application is something that my good friend Todd Price says is peel and stick. Basically, here's how the system works. This device that you see here, and there are several manufacturers of this device, is the transmitter. The method of transmission, the wireless link, can be a radio frequency to another receiver. But in most cases, what I'm seeing is more effective is a cell phone link. Now, that comes at a cost of, I don't know, $10 a month or something for the subscription. But you put a chip into this device and it has a cell phone link to the internet. You set the transmission rate typically at, you collect all the data and you boost it up there once every 5 minutes, 10 minutes, 30 minutes. It doesn't need to be every second because this is a pumping application. Not a lot goes on from second to second, but you want to be able to see what's going on in the field. And there are also trending parts of the graphical user interface that you see when communicating to this that will give you a trend over time. So this is the first thing you put on. You stick it on the side of the can. It's IP67. You wire to the VFDs Modbus port, and you allow the cell communication to communicate to a server on the internet. The next piece in the link is your smartphone, tablet, or laptop or computer that connects to that same server with an address. So, www.mydata.com, whatever, at which point you're going to be polled for a username and a password to get to your specific graphical user interface. This is in the sky. And then you have a graphical user interface that displays the data in an intelligent way on the device that you're viewing it with. Again, cell phone, tablet, PC, laptop, let's just call that the human machine interface or the HMI. Now, sorry, that little thing at the top always gets in my way. This is what the HMI can look like. This is what you would see on your cell phone, your HMI. What it's doing is it's pulling data from the drive up through the cellular link to that cloud, and you're able to see it because we have software on the graphical user interface, the GUI, to display it any way you want. If you will, you have the ability to put all sorts of different devices up there. This is a graph, this is a gauge, you've got temperature, this one up, that's not loaded in yet. You've got on-off indicator lights to tell you whether the drive is on or the fault is on. This could be blue, green, red, whatever. You have little symbols that you can use and make them rotate if you want to get fancy about it. You have on-off switches that you can use for the other half of this, which is control. So we have monitoring, which is data coming up from the drive that is displayed. And then we have control, which is the data going back down, which is your commands. Now, not all of the applications are monitoring and control. A lot of them are just monitoring. But as my good friend Craig told me, in his experience, he's seeing that the market is about 60% of the people doing this are also wanting to have control. Certain applications, it's not recommended to have control, but in a pumping application, there's really not an issue. You know, an issue would be if you had a crane or a railroad car or a paper mill. You don't want to be turning that on and off from your beach chair down in San Tropez. The fact that you have the ability, wherever you are in the world, to monitor your device and pick up the motor amps, the drive temperature to see if the drive's overheating. You have an output pressure sensor, you have a suction pressure sensor, and you have a flow sensor. And by the way, this is just 5 of 50 different things that we can put up here. And then you can make decisions and go to the control page, which is a different page in your graphical user interface, and you can tell the drive what to do. It may be that you can just turn it on. I can tell you that I'm going to put one of these on the roof of a house that I have, so that when the fire comes, I'm going to sprinkler that house. That's a whole lot better than me standing there with a garden hose doing it in the middle of the blaze. And wherever I am in the world, I'm going to be able to turn that pump on. It's an engine-driven pump, and it sucks water out of a lake. So I don't need the fire department or the electrical department. I just turn that thing on, and all of a sudden I got a shower on top of my house. So that's what you can do with this. Now, how hard is it to program these graphical user interfaces? Ideally, you won't have to, because we'll have a peel and stick solution that will be suitable to your application. But let's talk a little bit about that, because this is the conversation that I want to engender so that we get this peel and stick solution down pat. I'd like you to send me your input as to the data that you want to see coming off of a typical pump station, whether it's a pressure regulation station, whatever it is. I'd like to hear feedback from you on what you want to see on this graphical user interface, because it's really this easy. We're in edit mode, so I can take one of these things and I can configure it. I'm going to call it tank level, if I can spell. I'm going to pull this data out of one of any of these data inputs. This is the VFD. This is the IQ 1000 and the IQ U1000. All the data that's on the drive is available to me. How about if I just actually do kilowatt hours, or there's my PID feedback. Okay, so I'm going to choose one of these data points, and at that point I can set my red, green, blue. So let's say that 100% we want yellow. 80% we want yellow, which is warning, and 90% we want red, which is bad. And did I do that right? Minimum value 0, transition 80. Oh no, I didn't do that right. Huh. See how easy it is to program? Okay, so now I'm green up to 90%. From 90 to 100%, I'm yellow. Above 100%, I'm red. And then I can add this item to the graphical user interface. There it is. Everybody knows how to scale things, right? Make it as big as you want. And you've just put a data point on your graphical user interface. So again, in summation, we've got the peel and stick unit that basically goes on the side of the VFD. There's a cell phone chip that goes into this. It boosts the data to the internet. You log in with your HMI. You therefore get access to this graphical user interface. And we have designed the graphical user interface such that it gives you the data that you want. This is what I want you to talk to me about. Tell me what kind of data you would like to have on these graphical user interfaces. What we have here is a typical dial. We can have a bar chart. This is a data over time trending chart. My preferred way of displaying data is twofold. I'll give you the instantaneous data on the graph. Here we're saying output pressure is green up to about 75%, and then from 75% up to 90%, it's yellow, and above that, it's red. I can also put a green and red light here that tells me when I go into the red zone if I want to. This is the data over time chart. So it tells me what's going on over the past, some history, if you will. So I get the instantaneous data and I get the history. I like this. Other people may like it a different way. I'd like you to tell me what you would like. And at that point, we will be able to offer a standard graphical user interface that doesn't need to be modified. That's the peel and stick solution. Mount the unit, communicate to the internet, and then the peel and stick graphical user interface shows up on your HMI, your cell phone. Now, the other thing that we can do with this unit is, instead of just this one, which is an IP67 mounted on the outdoor, just mount it, put a sun cover on it. There are other devices from these manufacturers that come. Okay, yeah, my screen's a little bit slow. There are other devices that come with physical I/O to talk to things other than the drive at the site. Here, this unit, by the way, has to be mounted inside an enclosure because it's got exposed terminals. But I can wire non-VFD devices to this. I can wire pretty much anything, any analog signal from any sensor. So this is the previous unit with additional I/O capability. And most of the manufacturers out there who offer these wireless nodes, if you will, offer both versions. Now, I will say this. We can use this and wire the other non-VFD devices directly into the node and boost them up and show them on the graphical user interface. Or what we can do is we can go back to this, sorry for the update rate, robust outdoor unit. And let's say you have a couple of other analog sensors. As you know, the IQ1000 and the IQ-U1000 have analog inputs. You can wire them directly to the drive and via the Modbus communication, get that data up to the internet. We have the ability on the IQ product for up to 8 digital inputs and 3 analog inputs. We also have a pulse train input for pulse flow meters. So you don't even need to go to the unit from the radio manufacturer that has I/O. You just use the drive as an I/O port. That's a really nice thing about the Yaskawa product. We've had this extra I/O that you can use. And you have the ability on the drive to add an additional 16 digital inputs or another pulse input for 2 flow meters or some more analog inputs. So the drive can be your data collection center, and you can stay with the simple robust radio. Now, that we'll talk about much more, but again, I'm asking for your feedback. I really would like to see what kind of data you want on a typical pump station application. You may have some chemical metering data that you want coming in here, or conductivity data in the water, whatever. We can display anything you want, and you can see, even with my clumsy approach how easy it is to program the graphical user interface. But again, to repeat myself, I want to get the standard graphical user interface, the peel and stick solution out there so that 90% of the applications we've got you covered. It's okay if we have a couple of displays that don't operate because you haven't hooked them up. That's all right. You just ignore those. Okay, now in the last 5 minutes, I've mentioned something called IP67, which is the rating of this unit, and everybody's saying, well, what the heck is IP67? So I'm going to just take a minute to give you a refresher on what the international IP or ingress protection standards are and compare them to the American NEMA standards. In America, we always have a different way of defining things. The ingress protection standards are basically defined through the International Standards Organization, or ISO, and they consist of IP for ingress protection, and then in 90% of the cases, 2 numbers. The first number is your particle protection, dust, dirt, rocks, whatever. The second number is your liquid ingress protection. Now, these other numbers we can just ignore because they hardly ever happen in our industry. So for solid protection, the first number, you have 0, which is no protection. And then you can see this chart. By the way, I Googled ingress protection rating and got the Wikipedia. This is a Wikipedia sheet. So in the case of the IP67 rating of that little radio unit, you can see the 6 means no ingress of dust whatsoever. For the Yaskawa IQ outdoor enclosure, we are a 5. We have filters. The 6 means you're sealed. Now, again, as far as liquid protection or liquid ingress is concerned, Craig, are you still there? Did I lose the connection?
No, your connection's still good. It's just your screen not updating.
Okay, let me stop sharing the screen and start it again, because my screen just went black for a second. Fortunately, happened at the end of the class.
No, we can still see you and hear you.
Okay, so can you see the screen now?
Yes, I can.
Okay, great. So now we're talking about the second number in the IP rating, and that is our liquid level protection. Again, 0 is none. 1 is dripping water. 2 is dripping water when tilted at 15 degrees, which is kind of the NEMA 3R standard. Spraying water, splashing water, water jets, powerful water jets, right on up to 7, which is that device that I talked about was IP67, so no dust ingress, and 7 meaning you can dunk it into water up to 3 feet 3 inches. What is the IQ Yaskawa outdoor duty enclosure? Well, we say it's NEMA 3R because down here in the NEMA ratings, .3R is rain tight, but we all know that the Yaskawa unit also has a degree of dust protection. So it's more like a NEMA 3R, NEMA 12. So I have always said that we are IP54 equivalent. The water rating is 4 and the dust rating is 5 because it's a combination NEMA 3R and NEMA 12. So if we go back up to our charts, 5, 4, let's take the second digit first. 4 is we're good for splashing water, which means we're good for spraying water, which means we're good for dripping water or rain tilted at 15 degrees. And that's the second digit. The first digit in IP54 is a 5, which is thus protected, ingress of dust not entirely prevented, but must not enter in sufficient quantity to interfere with satisfactory operation of the equipment. So now you have a little bit of a review of what the international standards are for IP. I think it's a more definitive way of describing it. NEMA, NEMA's been around since I was out of college, and it's a little bit antiquated. I would tend to just try to translate the NEMA into the IP because the IP is a more modern definition. I hope that's been helpful. With that, it's 8 o'clock and time to go to work this Wednesday. We'll see you next week.
Thank you, Pierce.